Friends, welcome to the online course titled Offshore Structures Under Special Loads including Fire Resistant Design. We are now talking about the fourth lecture, which will be again focused on novelty of floating platforms. Just to have a leap over what we discussed in the last lecture, we discussed about the novelty by design of a tension leg platform. We will extend the discussion for a spar platform now before we move to discuss on floating platforms. A typical spar platform looks like this. Which has got multi-level decks, which will have the drilling derrick, which will have the flare boom, which may have the living quarters and others. So, this is maybe a drilling derrick, etc. This is what we call as cellar deck. This we can say production deck. This of course is the drilling deck. So, this becomes the top side detail where all other electromechanical equipments are housed. Now, the question is how this will be supported to the seabed. Let us say this may seabed. This will be connected by a cell shaft, which is nothing but a deep draft cylinder. Generally, because of the extensive length of the cylinder compared to the thickness of the cylinder, it undergoes vortex induced vibration. To essentially avoid this problem, they are strengthened with helical streaks. Just to additionally support this, sometimes there can be a mooring line, but it is not necessary. So, essentially the structural action of a spar is by buoyancy. It has got essentially a deep draft floating caisson, which is nothing but this, which is essentially a hollow cylinder. It is similar to a large buoy. If you look at the periods of the spar platform in surge, it is very flexible, which can go about 100 to even 120 seconds. Surprisingly, in pitch it remains relatively flexible, so about 60 seconds, and in heave about 25 to 40 seconds. Whereas, if you remember, in tension-like platforms these two were stiff degrees of freedom, the periods were very low, whereas in a spar they are considered to be flexible degrees of freedom. Now, let us see why such a discrete difference has been made in the conceptual form of a spar platform compared to TLP. The foremost difference between TLP and spar: TLP derives is restoring force from the mooring lines, or otherwise called as tendons. So, if TLP is anchored to the seabed, if TLP moves to the right, the tension in the cable or the tendons, the horizontal component encounters the wave, and the vertical component adds to its weight, that improves stability. So, the restoration essentially happens from the tendons, whereas spar does not rely on mooring lines. It resists by the deep draft cylinder only. We also said in TLP, because of reversal of forces which are axial in nature in the tendons, it can be subjected to a fatigue failure. Whereas spar does not have any such special difficulties. But spar has one demerit: installation is difficult. Because top side need to be assembled let us say commissioned only after the cylinder is appended, whereas no such issues are there for a TLP. Let us quickly see what advantages spar has compared to a TLP. Since it is more or less a free floating system, more or less similar to a free floating system, the responses in heave and pitch are lesser. One major advantage what spar has compared to TLP, for example, the drilling line or through the cylinder. For example, this is my spar platform, this is my cylinder, this is my drilling derrick. The drilling risers will be through the cylinder, which ensures a dry tree. So, this protects the risers. From wave action. It is a great advantage. It is simple fabrication. Most importantly, it has got unconditional stability. Why? Because the mass center is always located lower than the center of buoyancy, which ensures good stability. In sense, the stability is ensured even when the mooring lines are disconnected. Friends, you will realize that this case is not true in case of TLP, because in case of a TLP, FB exceeds the weight and FB and weight are compromised with initial tension. So, initial tension in the tether or tendons add to the weight, adds to the static equilibrium. Therefore, when tendons are removed, since buoyancy exceeds the weight, they will have a very large displacement. Therefore, drilling is difficult. Whereas, in case of a spar platform, it has got very high stability. Even on removal of the mooring line, they will still stay stable. Of course, spar platforms have disadvantages. As I said in the beginning, installation is difficult compared to other platforms. It is because topside can be only combined when the spar hull is appended. The second foremost issue is it has got a very little storage capacity. It is not meant for drilling. So, essentially it has no drilling facilities. So, spar platform are essentially used for storage and offloading, not for drilling. The fourth demerit is because of unusual length of the spar hull or what we call as a deep draft cylinder, it is prone to corrosion. That is the problem. Let us now move on to the novelty in floating structures. There are other floating platforms which are also constructed offshore. Most common platforms are used for exploratory drilling. Friends, there are two types of drilling one can do. One is called production drilling. Once the drilling wells are established and yield is confirmed, people start production, that is production drilling. To check whether the well can yield oil, people also do exploratory drilling. So, there are platforms constructed for exploratory drilling which are essentially of a floating type. One famous example which is commonly used for exploratory drilling is jack-up platform. They are called as jack-up rigs. They are suitable up to water depth of about 90 meters. The second type what we use for exploratory drilling is semi-submersibles. They are suitable approximately up to a depth of 200 meters. If you want to go for deep water drilling in terms of exploratory purposes, people modify the existing hull forms of the vessel and convert them into what we call as drill ships. So, drill ships can do exploratory drilling even up to a depth of 2000 meters. Now, let us quickly see what are those difficulties with each one of them. Jack-up rigs have specific difficulties. They are most vulnerable when afloat. If you look at the screen, a typical sketch of a jack-up rig is shown. These are the legs of the rig. The three lattice trusses are the legs of the rig. The what you see in the grey color is the hull. The hull has all facilities like living quarters, electromechanical equipments, heli deck, crane lifting, etc. So, usually when the jack-up rig is remaining afloat, these legs will be pulled off and the hull will be at the bottom and it will float as when the legs are pulled up. When the jack-up rig reaches the site, by extra ballasting, the hull is pulled up, at the same time the legs are driven into water. That is why it is called jack-up rigs. So, this figure shows the platform in a raised position. Generally, jack-up rigs are vulnerable when they remain afloat. Therefore, under towing conditions, they are susceptible to hurricane or cyclone damages. Coming to the part of semi-submersibles, please pay attention to the figures shown in the slide now. So, typical semi submersible shown here, which has got all topside details as that of a drilling platform. It has got a drilling derrick, it has got multi-level deck, it has got the flare boom and the cranes supported on columns and pontoon members, which remains it afloat. When they reach the position, they will be anchored or moored to the seabed. Mooring can be done either with the help of GPS, that is gravitational positioning system, or one can also use the mooring lines. Interestingly, as we move forward, we now realize that offshore platforms started with a geometry of fixed base. There were some difficulties, therefore, new semi compliant type platforms were launched. These platforms had very limited recentering capacity. They also had what we call by design a single point failure. Then people moved on to compliant platforms. They actually resist the loads by excessive buoyancy, but there were issues related to fatigue failure or extensive corrosion of submerged hulls. So, the improvement then led to formulate completely floating structures. So, friends, one can see a very clean novelty which has happened in the structural form of offshore structures, starting from a fixed type which has got TLP, jacket platform, gravity based structure, to that of completely floating platforms. The most common floating platform is FPSO. FPSO is floating, production, storage and offloading. So, it has got both the facilities, production facility and storage facility. FPSOs actually are nothing but refined or modified form of tankers or cargo vessels. The foremost functional novelty in FPSO is production and storage of hydrocarbon. Usually FPSOs are ship shaped geometry. One may ask me a question, why they are ship shaped geometry? Because it is very clear in naval architecture that ship shaped hull forms are proven to be stable both when they are afloat and when they are moored. However, when you want to do exploratory drilling, FPSOs need to be moved. There are two ways of moving them. One can be a permanent mooring, with the help of cables. The help of cables can improve their lateral stability against extreme storm conditions. Floating structures have some special attractive features. There is a minimum environmental hazard caused by a floating platform. Because crude oil can be disconnected and moved to the shielded area. When there is a severe storm. The second advantage could be lower turret system, with moorings are located below the wave zone. And therefore, not affected by storm. The third attractive feature could be the mooring system and the associated turret system are smaller in size they are useful only when FPSO need to be moved, because FPSO can otherwise stay afloat because they are designed to stay afloat in a stable condition. There are many advantages we have under floating platforms: very low cost due to high mobility, they have a very reduced lead time. FPSOs can be hired and they can be used at different locations. They have a very quick disconnecting ability. In case of storm weather. It requires a very little infrastructure, because you know only the existing hull forms are modified. Of course, they have some demerits. They are useful only for small fields. Large oil production fields cannot be commanded by an FPSO or any floating platform? They have a very low deck load capacity. Since risers are exposed, the drilling risers, wave action, they can be damaged. It has a very little oil storage capacity. So, you need to actually offload the explored crude oil to some shuttle tankers for further processing. So, friends, we had seen different kinds of structural forms. Their necessity for improvement, reasoning for change in structural action, their functional novelty, their load carrying capacity, their recentering capacity, their lead time for commissioning, and time for decommissioning. Having said this, before we try to understand what are the special environmental loads which can cause damage to these kind of platforms, let us speak something more about specific kinds of failure that happens in compliant structures. Very briefly we will talk about this. We will take an example as a tension leg platform. There are some special problems associated with tendons or let us say teethers of tension leg platform. What should be the design objective for designing a tendon of a TLP? Let us ask this question. What are the design objectives of tendon of a TLP? There are three objectives. The first objective is fatigue damage caused by the change in pretension should be checked. It should not fail by fatigue. Initial pretension, what we say as T0, should remain always positive. What does it mean? It means that the tendons should not slack. If slackening happens, tendons will fail by buckling. So, that is an important failure mode what we have in one of the commonly used complaint structure, which is tensionless platform, which is a foremost design objective. The third objective, as we all know, the maximum axial tension should not be more than the allowable value, otherwise it may result in tether or tendon pull out. Before we understand furthermore complexities in terms of estimating of loads on these structures, let us ask a question. In case of a tendon, what could be the kind of material used? To answer this, let us ask the first question: what would be the concept of design of TLP? The conceptual design of TLP is buoyancy should exceed many times by weight. In fact, buoyancy and weight should be equated by initial tension in the tethers. Buoyancy force which act upwards, weight of the platform which act downwards. Since buoyancy exceeds the weight, T0 also acts downwards. So, what does it mean? This means that part of the total weight of the platform is supported by T0. Therefore, it is necessary to reduce this value as far as possible, because more the value, more the axial stresses, more the fatigue failure, more the pull out. So, what material is generally used? Commonly used material is steel. People use hollow tubes as tendons. Usually these hollow tubes are air filled at atmospheric pressure to reduce their weight in water. The ratio of diameter to thickness is usually kept of the tendons is usually kept between 20 to 30, where D is the diameter of the tendon. You can say external diameter, T thickness of the tendon, otherwise called as wall thickness. The derivative values or further decreased, maybe the lower value 20 is used when you go for tendon commissioning in ultra deep waters. People also use stepped tendons where the larger diameter is used towards the upper end. Tendons need to support axial stresses and external pressure from sea water waves. Recent application for tendon material is carbon fiber composites. The specific gravity of carbon fiber is about 1.59, which is slightly more than water. This enables reduction of weight of tendons, the carbon fiber composites also have good fatigue resistance and high capacity to withstand static loads. More information can be seen from the recent studies conducted by C. Sparks et al. 2003, carbon fiber composites, tendons for deep water TLP, Offshore Technology Conference, 5th to 8th May 2003, Houston. So, friends, we are slowly now understanding different structural forms that are required for offshore platforms to stay in position. What are the kinds of loads generally act on these platforms which are conventional, for which these members are usually designed with international codal provisions. However, when special loads act on these structures, their behavior is entirely different, which even challenges their existence in even normal sea states. So, our intention in this course is to make you to understand what are those response behavior novelty of these platforms under special environmental loads, including fire resistance, which is one of the important agenda and objective of this course. However, without understanding the structural form and the conventional behavior under normal loads, it is not advisable and interesting to really know the response behavior under special loads. As a matter of fact, we should do couple of exercise problems to really understand how to compute the natural period, the restoring forces, the stiffness offered by the cable and mooring lines under these kinds of platforms by simple examples which we will do in the next lecture. So, in this lecture we summarize that we discussed about spar platform, we conceptually extended the comparison of spar with tension leg platform, then we moved on to floating structures. There we discussed about platforms which are used for exploratory drilling. We also understood what would be the special kind of material used to overcome fatigue failure, etc. in this lecture. I hope we are able to now understand different structural forms used for offshore production and processing under normal loads in normal sea states. How do they behave? So, we will take up some examples to understand them numerically, then we will move on to special kind of new generation platforms which are again redefined modified structural forms which are more advantageous than these conventional platforms. Thank you.